Thank you very much. So first of all, I thank everyone for the organizers for inviting me. I'm sorry I'm not there in person. As some of you know already, I broke my foot over the past weekend, and I'm not able to travel at the moment. But I have been attending some of the talks as much as I could. I have a question, first of all, for the audience. Can people see my cursor?
Yes.
Okay, good. So I'll use that then as a pointer. Okay, so I am talking about turbulence, and it's sort of obligatory in a talk about turbulence to give a quote from Feynman, as Nigel did the other day. So here's my quote from Feynman, the Feynman lectures on physics, where he says, finally, there is a physical problem that is common to many fields. It is very old. It has not been solved. It is not the problem of finding new fundamental particles, but something left over from a long time ago, over 100 years. Nobody in physics has really been able to analyze it mathematically satisfactorily, in spite of its importance to the sister sciences. It is the analysis of circulating or turbulent fluids. Okay, so this is what Feynman said. False. Okay, so I'm going to try to convince you that this statement is in fact wrong, and that there was a very exact mathematical analysis of the high Reynolds number limit of turbulent fluids that was done even before Feynman made this remark, and it was by someone he knew very well, Lars Onsager. Okay, so Onsager studied turbulence in the 1940s, and I have here a remark at the end of his 1949 paper, which I'm just going to read to you again quickly. And then the basic point of the talk is to explain this remark. So he says, it is of some interest to note that in principle, turbulent dissipation as described could take just as readily without the final assistance by viscosity. In the absence of viscosity, the standard proof of the conservation of energy does not apply because the velocity field does not remain differentiable. In fact, it is possible to show that the velocity field in such ideal turbulence cannot obey any Lipschitz condition of the form that he writes here. For any order n greater than 1/3, otherwise the energy is conserved. Of course, under the circumstances, the ordinary formulation of the laws of motion in terms of differential equations becomes inadequate and must be replaced by a more general description. Okay, so this remark might sound somewhat mysterious. I'm going to try to show that it's actually very simple to understand. If the outcome of my talk is that at the end everyone says, well, that's obvious, of course, then my talk will have achieved its goal. This entire talk could be about incompressible fluid turbulence, because even in that context, Onsager's ideas are still not widely known and appreciated, and it makes a lot of predictions going well beyond the classical Kolmogorov theory of 1941, including things like local versions of the 4/5 law for individual realizations of the flow without any statistical assumptions at all, no homogeneity, no isotropy, nothing, simply the assumption of high Reynolds number. Even more exotic phenomenon like spontaneous stochasticity. I won't have time to talk about those here because I'm going to, as I was asked to, talk about something of astrophysical relevance, which means that I have to put in at least magnetic fields. And also, since most astrophysical plasmas are compressible, I also have to have compressibility. And so sort of the simplest model of any astrophysical relevance is what I've shown here, which is the compressible MHD equation, but with a general equation of state. So I'll allow any general equation of state. And here I've just taken these equations from Landau-Lifshitz. Okay, so in this context, I'd now like to explain Onsager's remark and try to make it obvious what he's talking about. Okay, so he was talking about turbulent dissipation. Here is the dissipation appearing in the balances of mechanical energy, kinetic plus magnetic. And you see that there are those viscous terms that remove mechanical energy. Of course, because of total energy conservation, whatever disappears there reappears as internal energy in the second equation. And then similar equations appear in the entropy balance. And Onsager was discussing the fact, which was already to some degree confirmed experimentally in the 1940s, that these things have so-called dissipative anomalies, that is in the limit of very high Reynolds number, or formally, where all those transport coefficients go to zero, those dissipation terms do not vanish. For MHD, we have some confirmation of this coming from numerical simulations of incompressible flow by Manini and Poquet. So we do have an empirical basis for this statement there. We're actually fortunate for the compressible case because there are exact shock solutions, both for neutral gases and for MHD, that exactly exhibit anomalies of the type that I'm discussing. And the analysis that I'm going to present here applies, among other things, to such shock solutions. Okay, so first of all, in what sense are these anomalies? Why do we talk about an anomaly? Well, the point is that in the infinite Reynolds number limit, where all these transport coefficients formally vanish, you would naively expect to get ideal equations. And the ideal equations, ideal MHD, are Hamiltonian. They can be derived from a least action principle. Here I've written out the form of the action for ideal MHD with the generality I'm discussing. The point is that the entropy conservation is built into this variational principle. You'll see here that this entropy doesn't depend on the time in the action, and so the entropy is automatically conserved for a smooth solution of ideal MHD. Likewise, I should mention that there's magnetic flux conservation built into this variational principle, because the magnetic field that appears here is given by the formula that's right here, which expresses the flux frozenness. So you have actually an infinite number of conservation laws for ideal MHD, which it turns out are associated to the relabeling symmetry of the ideal MHD action. Okay, so the point is that when entropy production, among other things, does not vanish, that appears to contradict the validity of an ideal MHD limit. Okay, so it turns out that in fact, there is an ideal MHD limit, but now I need to sort of discuss how that comes about and Onsager's analysis of the problem. So first of all, the simplest thing that must happen in order to have a dissipative anomaly is that all the gradients of these fields must diverge. And that's obvious, because if I look at these expressions here, if they don't vanish in the limit where kappa, eta, zeta, and gamma, the magnetic diffusivity, go to zero, the gradients must diverge. So that doesn't need Onsager. Anybody can see that that must be true. So what Onsager realized is, first of all, this is a ultraviolet divergence in the sense of quantum field theory. We would now call it an ultraviolet divergence. Onsager called it a violet catastrophe. And in order to get a dynamical description in this limit, we must regularize that divergence. So Onsager didn't use the regularization that I'm going to talk about here, which is a coarse graining or block spin regularization. I don't have time to talk about the history of this. Onsager actually did something mathematically equivalent to this. He used what's in field theory called a point splitting regularization. He never published his proofs of any of the statements that I'm talking about. He had them, but they were buried in his notes, and he just told people his results and left them to reproduce them. But in any case, the point is that you have to regularize this divergence. The simplest thing to do is just do a simple coarse graining regularization by spatially averaging the fields over some length scale L. So if you do that, then of course all these gradients are regularized. And so if the fine grain velocity gradient blows up, this coarse grained velocity gradient remains finite in the limit under very modest assumptions. So for example, as long as the magnetic energy stays finite in the limit, then the gradients have to remain finite. Okay, so this, however, introduces a regularization scale into the argument. And one of the basic points of Onsager's argument was the fact that the physics cannot depend on this regularization scale. And so Onsager, in the 1940s, had really discovered some of the basic ideas of what are now called renormalization group and renormalization group invariance. Okay, so I'll show you how that actually was used in his argument. Okay, so if we go back to the equations of motion, it's very easy to regularize, I mean, to let the regularization act on them. This coarse graining operation commutes with all space and time derivatives. So all I have to do is put a bar over everything, and that represents the coarse grained equations. And so I haven't done much, but now the essential point is that if I keep that regularization scale fixed, L, and then I let the transport coefficients get small, then all of the viscous terms, the dissipative terms, the magnetic diffusivity terms drop out at fixed L, fixed regularization scale. So here I show you that specifically for the shear viscosity term, and it's a very simple Cauchy-Schwarz inequality that shows you that in fact that term is bounded pointwise by something that is depending on the shear viscosity, which goes to 0, and another term, which is actually the heating from the shear viscosity effect. So the point of the argument is that even if this thing remains finite, so even if the viscous dissipation remains finite in the limit, nevertheless, all the viscous terms in these coarse-grained equations drop out and go to 0. And the end result is that you end up with equations in which at fixed length scale L, those dissipative terms no longer appear. And in that sense, the scales at L and above are described by ideal MHD equations. Okay, so this is a statement which you will often see made in the literature that in the inertial range of scales, that's what we're talking about now, in this inertial range of scales where we can ignore the direct effects of the dissipative terms, the molecular dissipation, ideal equations hold. And so here, this is the sense in which ideal MHD is valid in the inertial range. And if this were true, so if we take pass to the limit where those transport coefficients really go to 0, this is a mathematical idealization of reality where they're not 0, they're merely very, very tiny. But if we actually pass to the limit and then these equations hold at all length scales L, then that's equivalent to what's called a weak or distributional solution of ideal MHD, and what Onsager called a more general description than standard differential equations. But now the question comes, if the ideal MHD equations hold, then in what sense can you have dissipative anomalies? So how is it possible that you can have energy dissipation still occurring? How can you have entropy production when you have ideal MHD equations valid? And we know that once I coarse grain, entropy production is still going to be happening because, for example, in an ideal gas, if I have entropy production increase, that means the large scale temperature is going to increase. And I can see that even with coarse grained observations. So the presence or absence of large scale entropy increase doesn't depend on the eyesight of the observer. That is in this arbitrary resolution scale, which has been introduced to regularize the divergences. So now the question is, where do the anomalies come from? Well, the point is that ideal MHD in the sense that we're talking about here is not the standard sense of ideal MHD. And to emphasize that point, I have rewritten the equations that appear here. I've just rewritten the equations. I haven't changed any of the equations. They're still exactly the same. All that I did is I took all those barred things and I decomposed them into uncorrelated parts and cumulant parts. So if you look at the bottom equation, for example, here's the simplest example where I took the 2-point thing, F1, F2, barred it, and I decomposed it into an uncorrelated part and cumulant parts. And this is ideal MHD in the sense that it's valid in the inertial range of a turbulent flow. Okay, now this is not the standard sense of ideal MHD. To emphasize that point, let me put all those cumulant terms in yellow. If ideal MHD held for the coarse-grained variables in the naive sense, then all those yellow terms would be gone, and then what I would have left are those black terms, and then the large-scale equations, the coarse-grained variables, would satisfy ideal MHD in the naive sense. But those terms are not gone, they're there. And so this is a really important, but I mean, it's a very simple point, but it's very important, is that the equations you're looking at are ideal MHD in the sense that it's valid in the inertial range of a turbulent flow. Okay, so let me rewrite that. This is so complicated, it looks really messy. Let me rewrite it a little bit to make it more compact. And all that I've done is I've taken all those cumulant terms and I've now introduced new expressions. Let me talk about those expressions now in red. For example, I introduced here a turbulent stress. So that's given by this formula here. This is the momentum transport by the small scale turbulent eddies, which have been eliminated by the coarse graining. Likewise, there's a turbulent electromotive force, a turbulent electric field, which is the electric field generated by the eliminated small scale motions. There is also a turbulent internal energy. And the origin of this is that in addition to the usual internal energy, there are also turbulent fluctuations of both velocity and magnetic fields. And with only coarse-grained observations, you can't distinguish between thermal fluctuations and turbulent fluctuations. And so that renormalizes, if you like, the internal energy of the flow. And lastly, there is this term JH, which is a turbulent enthalpy transport. And this is the transport of enthalpy or heat by the small-scale turbulent motions. Okay, so it's important to emphasize that these are ideal MHD effects. All these terms do not involve any direct action of viscosity. And I'm still talking about ideal MHD. The only sense in which ideal MHD applies in the inertial range of a turbulent flow is the sense that I'm talking about here. So these are exactly the terms. We had some discussions earlier today about large eddy simulation. These are exactly the terms that somebody in large eddy simulation would want to model. And Onsager's theory, I should say, provides the mathematical foundations for large eddy simulation. Okay, so let me go on and look at now the balances and understand how those terms can produce anomalous dissipation. Okay, so let's look, for example, at the resolved mechanical energy balance. If I look at the resolved mechanical energy balance, because of the appearance of these terms, these renormalizations of the ideal MHD equations, I get new terms in the balance, and so the mechanical energy, kinetic plus magnetic of the large scales, is no longer conserved. There's now a sink term, and this sink term I've written out here explicitly. And this sink term is just the mathematical manifestation in this coarse graining analysis of turbulent energy flux. This is energy cascade right here. So the reason that kinetic energy and magnetic energy are not conserved in the turbulent flow is because there's cascade. There's both a deformation work term, there's a cascade of magnetic energy, there's also another cascade term associated with specifically the compressibility effect, and those take the energy from the large scales and they transfer it to the small scales. Okay, so that is the essential mechanism of what produces these so-called anomalies. Now, if you only stopped here, I think that this wouldn't be too much. The key point that Onsager realized is that this energy flux yields a kind of deterministic Kolmogorov 4/5 law for individual flow realizations without any statistical assumptions at all. And I'm not going to have time here to talk about the connections with the traditional 4/5 law and how this generalizes it in some ways a very great deal. I'm only going to have time to sort of sketch the main idea here. But the real point is that all of these expressions, all of these cumulant terms can be rewritten in terms of increments. And this was the fundamental realization that Onsager had in a somewhat different mathematical form. And so here I've written out this result for this second order cumulant. And it's an easy identity to check. Once you know that it's true, you just substitute the gradient, the increment, carry out all the multiplications, and you'll see this reduces to the definition that I gave before back here at the bottom of the screen. Okay, so once you know it's true, it's easy to verify. You just have to be smart enough to know that it's true. With that result, you can now take all the expressions that appear in Q flux back here and rewrite them entirely in terms of increments. Okay, so here I took the mechanical energy flux term, and the turbulent electric field can be written in terms of a velocity increment times a magnetic field increment. The magnetic current in the electric current in the large scale can be written in terms of this magnetic increment divided by L. You put that all together and you get this type of an expression for the magnetic energy cascade, which is of the form of a 4/5 law, an increment cubed divided by L. Now, since we know that the dissipation that we're observing cannot depend on the scale of resolution, that means if there is non-vanishing dissipation of the limit, it should appear when we take first the transport coefficients to 0, and then subsequently take the limit as L goes to 0. So again, this is where we're using the renormalization group invariance. We're making a good choice of this renormalization scale. We're setting it to 0. We should still see dissipation in the limit. And if you look at this expression, it's very easy to see that you cannot stay smooth. In particular, if all those increments scaled linearly, this would go to 0 like L squared. But in fact, you get sharper inequalities than that. Here is sort of the simplest inequality you can get that said scaling exponents of the velocity field and the magnetic field have to obey an inequality of this type. This is the generalization of Onsager's result on 1/3 scaling for the velocity. So Onsager's claim was that you need Holder exponents, that's the mathematical term, Holder exponents of the velocity field less than or equal to 1/3 somewhere in the flow in order to get anomalous dissipation in the infinite Reynolds number limit. So here I'm doing this in terms of scaling exponents, but I'll emphasize I'm not doing any ensemble averaging, no statistics. All I'm doing is local space averaging, and that's enough. And I don't even need scaling. I just need upper bounds of this sort. And that's the kind of result that you derive is it's a statement about the kind of singularities in the flow that are necessary to generate anomalous dissipation. Okay, so the same analysis that I just did for this middle term, coming from magnetic energy cascade, can also be done for all the other terms, and you can get 4/5 law type expressions for all of them. I will mention that there's one surprise for the compressible case that has no incompressible analog. And so I want to, since I'm talking about compressible magnetized systems, let me emphasize some of the new features that result compared to the incompressible case. It turns out that this energy flux actually does not match on to the viscous dissipation, the dissipation from Joule heating and viscous dissipation, which is very different than the incompressible case. It turns out that there's an entirely new source of anomalous dissipation associated with pressure work. And it's actually something that happens in shock solutions. So shock solutions, it turns out, is sometimes said, but without much justification, for compressible flow can in fact short circuit energy cascade. And I'll emphasize that this new source of energy dissipation cannot be gotten from any of the traditional large eddy simulations. So it doesn't matter how you model any of these red terms that appear here, they cannot give you this new source of anomalous dissipation. It has to be modeled separately. And again, it can be associated at shock solutions that begin to appear at higher Mach numbers. Okay, so that's sort of one new surprise, one new feature that comes in from compressibility. But I'd also like to discuss something else which is novel that hadn't been discussed before, and that's the entropy balance. Okay, so the entropy is also naively conserved for ideal MHD, and I can do a similar analysis there. And it turns out that this expression right here, which I call intrinsic resolved entropy, is a nice regularization of the entropy. Now, you might ask, why do I add this extra term, which is coming from the unresolved mechanical energy, kinetic and magnetic? I don't have time to explain this, but it turns out that if you don't add this little term in, if you just take the entropy of your fluid, of the compressible MHD coming from the equation of state, and you put in those coarse-grained internal energies and coarse-grained mass densities, you don't get fully regularized expressions. When you take the time derivatives, you still get terms that come from the molecular dissipation. And this is actually something that took quite a bit of time to work out, but we realized by adding this correction term in, you actually fully regularize this expression. That's technical, but important. But then the whole rest of the argument goes through, and then you can take a time derivative, you can get a balance for this intrinsic resolved entropy, and it no longer has any dependence on the microscopic dissipation. I write out all these things here. This is entropy flux. Okay, so in complete analogy to energy cascade, you also have entropy cascade, and here is the detailed expression for it. It's got sort of actually five different terms associated to various physical effects arising from the turbulence, including the heat transport, the mass transport, the temperature gradients. All these different terms appear in the turbulent production of entropy. Okay, and so I should say, this is unlike the kinetic energy. There is nothing else you can prove this. There is no other way to, I mean, shocks don't give you any way of getting the anomalous entropy production, even for things like shock solutions. This is it. There's no other extraneous source except flux of entropy. Okay, now, as I said in the Onsager theory, you don't need ensembles. You never need to talk about ensembles, but you can always introduce those as a special case. And so to put this in a more familiar context, let me just say briefly what happens if I have a statistical steady state where I maintain a statistical steady state by removing the entropy produced at small scales by introducing a cooling function at large scales. In that case, you can easily see that this inertial range cascade, this inertial range entropy production, if I just go back to the steady state and I take the ensemble average of this equation and I add an extra cooling term over here, then the large scale cooling, okay, has to match that inertial range entropy production. But if the large scale cooling really is confined to the large scales, then that's equivalent to the microscopic cooling, which is also given by the microscopic dissipation. And therefore, you get an entropy cascade, which takes the entropy produced at small scales and cascades it up to the large scales. Okay, so you actually get a very simple, nice physical picture here that entropy, which is produced at small scales, cascades up to large scales. Or you could also say it in the reverse way, that large scale negative entropy or negentropy, which is produced by large scale cooling, cascades to small scales where it gets canceled by the microscopic entropy production. And this picture generalizes a theory of Abakov in 1949 for incompressible flow in sort of several fundamental ways. He considered only sort of one possible source of this entropy production that appears in the incompressible case. And here we have a sort of more general picture for the fully compressible flow. Okay, now, just as in the case of energy, you have 4/5 laws. And so all these expressions for entropy flux that I wrote over here can be written in terms of increments. And this allows you to, again, say that you need singularities of a certain specific type, basically, roughly Kolmogorov type or worse, in order to cascade entropy. So shock solutions, they definitely have enough singularity. They're more singular than Kolmogorov, but other background Kolmogorov singularities, Kolmogorov type singularities, will also suffice to cascade entropy to large scales. Okay, now let me just make a remark here. I don't want to spend too much time on the entropy because I'd also like to get to magnetic fields, but let me just say that there have been previous discussions of entropy in the context of compressible flows. A very common theoretical approach is to linearize around a background solution and to introduce so-called wave modes. And the wave modes that are typically introduced for MHD, compressible fluids, or even also, there are additional modes for compressible MHD. Let me here just talk about the original compressible neutral gas. You've got vortical modes, entropy modes, and sound waves. And this idea of Kovasny was that the entropy is simply cascaded as a passive scalar, and this leads to a forward cascade of the entropy as a passive scalar. this is exactly the opposite conclusion of what comes from our exact analysis, where we find that the entropy actually inverse cascades to large scales, from small scales back to large scales. And this Cavazzi linear mode theory is sort of in fundamental conflict with the second law of thermodynamics. We're going to have a talk later in the week discussing waves versus structures. I would say that this entropy mode analysis is sort of taking the wave notion to sort of its extreme limit, where it really becomes absurd, and it's sort of contradicted by the analysis I'm presenting here. Now, this plays some role in discussions of astrophysics, for example, in the interstellar medium, where a number of authors, Higdon back in the 1980s and Lithwick and Goldwright, have proposed that this forward cascade of the entropy mode actually might be responsible for this big power law in the sky that actually appeared in a couple of the other earlier talks. And they even introduced this notion of what they called a cooling catastrophe, where because the entropy mode is strongly damped in isothermal flow, it wouldn't allow these fluctuations to exist. But as a matter of fact, our analysis is quite the opposite. And we find that large-scale cooling, in fact, introduces negative entropy, which requires cascade. In order to alleviate that excess negative entropy at large scales, you have to have a cascade of that negative entropy to small scales, which requires fluctuations. So it's really quite the opposite. And I would say that whenever you have a gap between the scale at which entropy is produced and the scale at which entropy is removed by cooling, then this entropy cascade is inevitable. And so the interstellar medium is a quite complex picture, but whenever there is this gap in scale between the large scales where you have strong cooling and isothermal approximation might be valid, and the scales at which entropy is produced at small scales, then entropy cascade is inevitable. It must happen. Now, I do want to emphasize one important fact about the interstellar medium, and that is that like the bottom 1/3 of this graph is actually collisionless. So the collisional scale, the mean free path length for, say, the warm phase of the interstellar medium is like 10 to the 10 meters. That's sort of around here. So the model that I've been using so far to talk about turbulence is actually invalid at these small scales. And we're actually there talking about a collisionless regime. And so all of the hydrodynamic theory that I presented so far doesn't work in the small scales of the interstellar medium, as well as a great many other kinds of astrophysical plasmas, including the solar wind. So what I want to say now quickly is that all of the analysis that I've been talking about here also carries over quite readily to kinetic plasma turbulence. And so let me just discuss that as quickly as I can. Here I've written out sort of a standard set of equations for a collisionless plasma of multi-particle species. And I'm going to take the Landau collision operator here that represents the effect of Coulomb collisions. I've got the usual Maxwell equations. And the important thing is that this system satisfies the second law of thermodynamics, and there is entropy production appearing in this equation. Now, as I just said, this is a very collisionless plasma and also the solar wind. So you might still wonder, what is the small scale source of the entropy production? Well, there's a nice conjecture that was made already 25 years ago by John Kromis at Princeton, that in the limit of vanishing collision rates in a plasma, the entropy production may not vanish. And the analogy was already very clear in his early papers that this is exactly analogous to the hydrodynamic case of turbulence, where dissipation may not vanish in the limit of vanishing viscosity, for example. And so this is sort of the straightforward analog where in the limit of vanishing collision rates, entropy production may not vanish. And so we can take this conjecture and we can try to understand whether or not this is in fact described by ideal Vlasov-Maxwell, where we just drop these collision terms. And if so, how can that be consistent with anomalous entropy production. Okay, so everybody should be already primed by the hydrodynamic case to see how this is possible. I should mention that the Kromes and Hugh in their first work in particular mentioned the important role of this term here in the equation, that is the advection term, which produces phase mixing or Landau damping. And they pointed out that that could be an important source of growing gradients with respect to the velocity variable. This must be true. You must have diverging velocity gradients, as you can see from this diffusion equation, because if the velocity gradients don't diverge, then the entropy production will in fact go to zero. You can see that directly from this representation here. So we're exactly in the same frame as Onsager discussed. If we want a dynamical description in this collisionless limit where these gradients blow up, we have to regularize the equation. Here we do that with a coarse graining both in physical space and in velocity space. And then it's very easy to show by exactly analogous arguments as I presented for the hydrodynamic case, that if I keep those regularization scales L and U fixed, then in the collisionless limit, keeping those scales fixed, the collisions vanish. Okay, so the collision term drops out if I keep the length scales fixed. Now, again, this leads us to the question of, well, how can we get entropy production? Isn't this anomalous? Well, it is anomalous in terms of a naive Vlasov-Maxwell limit. The Vlasov-Maxwell equations are Hamiltonian. Here's actually the action function that was written down by Francis Lowe. And entropy conservation is built into this expression. So that follows just from the fact that the initial distribution here is advected by the resulting flow in phase space. So all moments, all functions of the distribution are conserved in time according to the simple variational principle. These are not microscopic conservation laws. These are emergent conservation laws that emerge in the collisionless limit, assuming that that limit is smooth. Okay, so now the question is, given the fact that we know that we have ideal Vlasov in some sense, how do we actually generate entropy? Well, the point is, just as in the hydrodynamic case, and these are not naive Vlasov-Maxwell solutions. They're Vlasov-Maxwell solutions in the coarse grain sense, where I put bars over everything. And so that means that the effective terms that appear in this equation have been renormalized, and I can introduce that renormalization here simply by introducing what I'll call a phase space Favre average, where I simply introduce the coarse graining weighted by the distribution function itself. And this allows me to rewrite this weak or this coarse grain Vlasov-Maxwell to look like the original Vlasov-Maxwell, but I'll emphasize that the V hat and E hat that appear here are not any longer the bare electric field and the bare velocity. They've been renormalized. Okay, so they're now renormalized quantities. And in particular, they no longer satisfy the Liouville theorem. So for the original case, because it's Hamiltonian, I satisfy a Liouville theorem. The flow in phase space is incompressible. It preserves volume. But that's no longer true for these coarse grain variables, these new renormalized variables. And so therefore, I now have entropy production, and I get a cascade of entropy through scales in phase space, both physical space and also the scale in velocity space at which I'm observing. Okay, so this can be worked out in more detail. Again, I can't go through the mathematics of this, but you get, again, by introducing increments into the expressions for cumulants, you can write all of the terms for entropy production, of which there are 4, in terms of increments, and you get 4/5 type law expressions for all of them. So these are the analogs of 4/5 laws for entropy cascade in kinetic plasma turbulence. The first one up here is the one that corresponds to linear Landau damping or phase mixing, but you also have contributions coming from the electric field and the magnetic field, and another extra term from the magnetic field, although that one is easily seen to be irrelevant in most circumstances. Okay, so these are terms that can be analyzed. I'll emphasize first that if I set the velocity scale proportional to the length scale, and I don't have time here to justify in detail why you might do that, but there's good reasons from kinetic theory that you might want to set U and L proportional. Anyways, we can do anything we want because they're arbitrary regularization scales, but this is a well-considered choice. If I set U proportional to L, those two factors cancel out here. And then you can see that as long as the distribution function remains even continuous in the limit, and in fact with much weaker assumptions than that, the Landau damping term is going to go to zero. So in contrary, yes.
Sorry, we're running out of time. Would it be possible to wrap up?
Yes. Okay. How much time do I have left?
Say a minute.
Okay. In that case, let's skip all the. So let me skip all the magnetic field stuff then. There's a whole stuff about reconnection that I don't have. Okay. But let me just say that this entropy cascade actually now has the prospect of being observed in magnetosheath turbulence. Here I present some observations from MMS in the turbulent magnetosheath, in the terrestrial magnetosheath, that show very, very complex ion distribution functions that actually have power law scaling in velocity space. These were reported in 2017 by Servideo et al. I'm now collaborating with those guys to measure all these four terms. We've already verified that, in fact, the linear Landau damping term does go to zero. It doesn't produce an asymptotic entropy cascade, but it's very likely that the other terms do. So I'm just going to pass very quickly over the reconnection. I'll just say that it's the same story. And there are many statements there that are made constantly in the astrophysics literature that because the large scales of a turbulent flow are described by ideal MHD equations or other such equations, magnetic flux is frozen in. This is false, okay? Simply because ideal MHD holds, the magnetic flux is not frozen in because it's not frozen in the usual sense that your grandfather meant. It's frozen in a coarse-grained sense, and this coarse-grained sense allows large-scale reconnection. And in fact, if there's reconnection of very large scales, of which I'm showing here an example from simulation, if there's reconnection of very large-scale structures in the solar wind, it has to happen whether I'm looking at small-scale eddies or not, because coarse graining is just a passive, filtering, a passive smoothing. It's taking off your glasses. And when you take off your glasses, it all comes from turbulent effects. Okay, so I'm going to have to skip all that. Let me just go to my takeaway messages and say that I hope what I've done here sort of explicates this Onsager theory and makes it clearer what it's about. I consider the Onsager theory to be sort of the standard model of high Reynolds number turbulent. It's something that everybody should know that is interested in turbulence in any situation for the high Reynolds number limit. It's not, however, still very widely known. There's exactly one place where it's taught, and this is my turbulence course notes at Johns Hopkins. I think this is the only place where the theory is presented systematically for scientists and engineers. You can read more about it there or at any of these other references. So thank you for your attention. Sorry, when I'm not directly seeing the audience, I get a little decoupled. So,
not to worry. So let's just do one question, and remember that because our speaker is remote, you have to use your seat mic.
So you talked about cooling in the interstellar medium, and how you assume that happens on large scales, but my understanding is that cooling is done by lines which happen at molecular or atomic level, so it's on very small scales, and I don't understand why you can say that that's large scale.
Well, first of all, it's not my assumption. It was actually the assumption also of Goldwright and Sridhar and many other people that the sort of the cooling is at large scales. So the question is where, so of course, it happens from atomic levels. I mean, that you'll have, radiation. But the question is, at what scale from the turbulent modes does it remove that energy? That's the question, right? So at what scales is the energy being most efficiently removed? And the point is that if you have a separation between that scale and the scale at which the entropy is produced, then this inverse entropy cascade is inevitable.
Okay, so let's thank the speaker again. I'm afraid we have to move on.
First of all, thank you so much to Blakesley in putting such a great workshop together. I think it's awesome to bring different fields together and get exposure really to different terminology and different aspects, maybe of the same process, right? But in a very different and innovative way. So I'm going to talk a little bit about this process known as raining onto black holes. So there has been significant advances in this decade regarding galaxy formation and evolution, and not only galaxies, but groups of galaxies, and as Luca was saying, also clusters of galaxies. So here is a simulation that many people show, and basically I start from high redshift, and so basically I'm taking very simple concept here, so minimal amount of equations, so to keep kind of the audience more engaged. And just here I want to show you the background, and basically at high redshift we have this collapse of dark matter halos, right, invisible matter, that basically forms these proto-groups, proto-galaxies, and so on. But what matters here for this talk, and in particular for us about turbulence and hydrodynamics and MHD, is of course the gas or the plasma. So most of the baryons basically collapse into these dark matter halos, and they form these extended hot X-ray emitting atmospheres. So we call them hot halos or X-ray halos, but they are really key to understand, of course, the evolution of the galaxies, groups, and clusters, and in particular, the evolution or co-evolution of black holes. So here is a collection of different hot halos, and Chandra XMM telescopes have given us beautiful images, again in X-ray. So hot halos emit X-ray photons via Bremsstrahlung. And so you see all these beautiful structures from shocks to bubbles, but for this talk, I will focus more on the turbulence aspect. So to convince you that basically hot halos are really key for the evolution of galaxies and supermassive black holes, here is an important plot. So first of all, for kind of the outsiders, so each galaxy group or cluster of galaxies at the center has a supermassive black hole with masses between 10 to the 6, 10 to the 10 solar masses. Okay, and so you see here black hole mass versus X-ray temperature. So you can correlate black hole mass with many, many properties of your halos, stellar component, dust component, or whatever, but apparently the X-ray temperature or the properties of these hot halos, these turbulent hot halos, are really key, and one of the tightest relation is between the black hole mass and X-ray temperature, even more than the stellar properties. Okay, so X-ray halos are really crucial to understand the evolution of black holes. So here is kind of a synthetic diagram that I use a lot, and I'm leading this program known as Black Hole Weather, which tries to link the inner supermassive black hole scale up to the scales of the galaxy group and clusters. So we are talking about roughly, not in scale here, but roughly 9, 10 orders of magnitude, right? So from the milliparsec up to the megaparsec. Megaparsec 10 to the 21 centimeter, okay? And there is a whole lot of interesting physics going on, complex physics, but really the remarkable thing that we learned definitely in this decade is that really turbulence is a key driver in both directions, both in the feeding part and also the feedback part, okay? So typically the program is divided into kind of the numerical part and the synthetic observational part, but given the audience, I will focus more here on the theoretical and numerical results. So I've seen lots of equations. We all know the MHD equations. We typically use these Eulerian MHD codes, such as Flash, Athena, Gamer, and so on and so forth. One key thing, so the Eulerian codes, as you know, the field is very mature, and essentially, we take advantage of this great feature, which is AMR, or additive mesh refinement. So you have many, many levels of grids on top of each other, not a uniform grid. And so you zoom in into the region of interest, for instance, from the hot halo down to the supermassive black hole. So, and given the basically exponential increase in computational resources, we can really have 20 or even 25, even 30 levels of refinement. So we'll focus here on this part, so the macro feeding or the condensation rain, precipitation, and this kind of, you should think of these hot halos really as analogs of our own atmospheres. So of course, these are plasma halos, but in reality, remarkably, they really behave, so to speak, as our own atmosphere. I'll show you later some more quantitative plot about this. But a step back, so to show you what happens. So I usually use simulations as sort of experiments. So I start with a simple box, no physics, basically. So just, for instance, here, adiabatic galaxy, of course, very idealized, and then I proceed injecting more and more physics to see what happens. So this is a cross-section in temperature of a massive galaxy, 1 kiloparsec, so roughly within the galaxy, but of course, the tiny black hole here is, several orders of magnitude inside the center, okay? So, and when you have a hot halo, adiabatic hot halo, no cooling, no heating, no turbulence, no rotation, of course. So very simple accretion, spherical symmetry accretion, very boring accretion. It's also called Bondi accretion, and here is the classic formula. So this is the accretion rate, normalized to the Bondi rate, and so basically, if you take a classic Bondi rate, which is, we know from the 50s, you get this kind of very simple, smooth, and very low level accretion rate. So typically here is 10 to minus 3, 10 to minus 4 solar masses per year. So very low level of accretion, very difficult to grow the black hole throughout 10 billion years. Okay. So now we start to see what happens if we inject our beloved turbulence into the box. And of course, you start to form all this vorticity. And injecting vorticity, of course, means that you have some, say, local angular momentum. And so it's very difficult, again, to put the gas inside the tiny supermassive black hole. Okay, so this is pure Bondi, and then the accretion rate is even further suppressed. So takeaway point is that in a, say, adiabatic hot mode, these kind of atmospheres that each galaxy has, but in a kind of idealized way, so the accretion levels are very low, very smooth. Okay, but this is definitely idealized, and we see this throughout basically the multi-wavelength observations. So we see hot halos not only in X-ray, but we see different residual structures within these hot halos throughout basically all the temperature range. What you see here are warm 10 to the 4 Kelvin filaments in a massive galaxy. We are starting also to see all these molecular clouds in the same halo. Okay, so really multi-phase systems and very complex nonlinear halos. So the more, say, realistic accretion and kind of how to model the accretion onto black hole is to use cold mode accretion, okay, because we see all these residual features. So classically, we had two very extreme models since 30 years. So because, of course, we didn't have very advanced simulations, so we had to have strong assumptions in the analytics. But basically, on the one hand, so let's start first here on this extreme regime, which is called the cooling flow catastrophe. And essentially, the inner core of the galaxy is going to collapse completely. If your halo is emitting radiation, it loses at the center internal energy, and so you have this catastrophe, and essentially your galaxy, an entire gas, is gonna to fall onto the black hole. This is never observed, so it would mean that basically you would observe black holes up to 10 to the 12, 10 to the 13 solar masses. We don't see that. Also, the opposite situation is when you have basically rotation, and instead here, of course, the gas condenses and collapses onto a thin disk, so-called disk accretion. And here again, the angular momentum barrier prevents your accretion. So very suppressed accretion here, and over there, kind of very boosted and kind of maximal accretion. However, we know that these halos are turbulent. So first of all, recently Hitomi has this new X-ray telescope, which has given us at least one observation. We see that at least in one halo, there is this velocity dispersions of the order of few hundred kilometers per second. So as absolute value, it's kind of significant, but in terms of the sound speed of these halos, which can be several hundred, so 500 or 1,000 kilometers per second, so this turbulence is still subsonic. Okay. So in this kind of hot halos, which are turbulent, okay, and definitely massive galaxies in all simulations, it's very difficult to have a very coherent halo, right? So, and in these turbulent halos, it generates this chaotic accretion mechanism, which was presented years ago in 2013. It's also called CCA, so it's always great to show CCA at CCA. And at the same time, basically, it's really simple. So the entire simulation, of course, has complex statistics, and you can go using the power spectrum analysis or all the different statistics that we discussed. But in simple terms, you should think of this CCA mechanism as analog of our own rain or precipitation here on atmospheres. And indeed, even if you take the ratios, the density ratios between the different phases, so hot phase, warm phase, and cold phase, they are really analogs also here to our own atmospheres phases. And so the key point is that on turbulent halo, as you know very well, you have some velocity dispersion, and so you create locally some density fluctuations, right? And where you inject a little bit of overdensity, of course, Drummond has shown that you have more cooling, right? So you create these thermal instabilities. So you form these extended warm filaments and cold clouds through thermal instability in a very recurrent way, especially when turbulence dominates over rotation. Okay. So and you have this kind of, so to speak, chaotic process. So yesterday I learned that turbulence is a soup of loops, or a loop soup. And basically, this is chaotic streamlines into this CCA process. And you can see here, right, how basically you have all these tangled loops and vorticity and so on and so forth, of course. But in particular, the center, so this is a stratified halo, so the turbulence tends to change a little bit. It's even more vigorous because you already have stratification. In the very center, we will see, or at least showing here, again, just the concepts, that basically these clouds start to collide inelastically, okay? But to give you just a brief summary here of kind of the entire process in a visual way. So we start, for instance, from the hot X-ray halo, which is highly turbulent. You see here, these are basically the galaxy, a single galaxy core. So in hard X-ray, you see all these turbulence fluctuations. In soft X-ray, you start to see all these condensation filaments that we see very well in the UV and optical phase. And these are sort of really not passive, but so to speak, tracers of your own turbulence. So really, if you go looking inside, so these really trace your eddies and vertical motions. So in the peaks of these warm filaments, 10 to the 4 Kelvin, condense further into molecular clouds. And these clouds within, this 100 parsec scale, they start to collide inelastically, continuously. And some of these clouds, they get head-on collisions, and they can cancel sometimes angular momentum. And so some clouds are funneled over the center, and you can boost your accretion rate. So the accretion rate is very different from all these classical modes, like we're seeing, right, thin disk accretion or spherical symmetric accretion. So it's really a chaotic process. To convince you that you can probe CCA in many, many different ways, and many people have done this independently in very different groups, and in excellent way too. And basically, but I want to show you this one, which I think is the most interesting and to me exciting, and less known to me, and maybe the experts here in the room know better about this flicker noise or pink noise. So whenever we take power spectra, but not in space, here in frequency, what we see most of the times on average, forget about the noise on top of the power spectrum, on average, most of the simulations show this kind of -1 slope, right? So this seems really very common in this process. And so going throughout the literature, so I'm sure you know better than me that this kind of noise, flicker noise, pink noise, is very characteristic of this fractal and chaotic phenomena. And to give you a sense of this kind of CCA rain noise, let's see if it works. Yes. So this is kind of directly from the simulation, and it's more or less this kind of thing, flicker noise. Okay, it's really what is falling onto the supermassive, and it's very soothing, for your brain noise. And indeed, it's incredible. You can spend hours and hours on that, and we basically not only see this kind of noise in the quasars, sunspots, and meteorological data, but you're basically, apparently, neural activity, heart, and even the stock market often behave like this. So up to you, the connection, and I'm very open to see all these interdisciplinary insights about that. So my simple takeaway is that nature shows this kind of simple noise because the variance of -1 slope is constant per each log interval, right? So it seems like variance is more important here. And to convince you of that, so since yesterday we heard about testing through AI, fantastic talk, I want to do the opposite, kind of human HI learning test, and I want to, so you heard the first sample from the simulation, so let's see if the other sample, out of sample, say, data compares well, and if you can see the similarities. Or here. So can you tell me what it is? Rain, right? Remove the bird, but it's soft rain, right? So, and indeed, so if you go quantitatively, this is more or less flicker noise. Yeah. Yeah. Is anyone disagreeing about this? So 100% success rate in human intelligence testing. And so in the last, 2 minutes, or 1 minute, so I wanted to show you the feeding part, but of course there is whole lot of science, and many people are actually working a little bit more on the feedback part, but essentially you should think of this system really as a self-regulated system. Again, turbulence remarkably seems to be the key, say, the glue between the feeding and the feedback part. So in the feeding we have seen, right, it drives this precipitation. So in the feedback part, focus here in this top panel. So again, it's a cross-section through the center of a massive galaxy in density, so fairly low resolution, but to show you the point that all these red clumps are your clouds and rain, and essentially they go down, and what happens is that the black hole does not like to eat actually this gas. And even if we go down with GR, MHD simulation, so very complex simulation, down to the horizon scale, most of the times the black hole re-eject back this mass in the form of outflows and jets. In this case, they are massive sub-relativistic jets. So you should think of this cycle of raining and then perpendicular, basically outflow and jet injection. Okay, between phases of cooling, a little bit dominating overheating, and then down to cooling being less than heating. Okay. And so there are many type of features, but again, I want to show you, so, and the cycle goes through all these kind of cavities, shocks, and uplift, but one key property, again, is turbulence. You can see here, again, cross-section, that essentially, when you inject all your jets and outflows, you create all this kind of local turbulence, and if you wait a little bit longer, different events create this, so to speak, macro turbulence, right? Turbulence is a multi-scale process, and essentially your injection, an isotropic injection of energy, at some point gets not magically. Initially, we saw it got kind of magically, but if you go down and you see the vorticity, the power spectra, and so on and so forth, you will see that really turbulent mixing is a key component to redistribute the entire energy over 4 pi. Okay, so I'll stop here, and essentially to recap a little bit what I discussed this kind of raining mechanism, and you should think this raining mechanism as analog of our own precipitation here on Earth. We have a turbulent environment, and out of this turbulent environment, the warm filaments and cold clouds condense here through thermal instability, and then they collide inelastically, say, in the central mesoscale, it's called, kind of parsec scale. And some of the clouds gets funneled toward the supermassive black hole. And here, only a fraction goes through the horizon, and most of the mass is actually re-ejected back in the form of jets and outflows. So a lot of science, of course, and a lot of studies here. We don't know many things of these things, but at least the core part we know is that there is some kind of self-regulation. So the outflows entrain more and more gas, and at some point, they deposit the energy at the macro scale, reheating the halo, and so basically stopping down the rain. So and you go through these cycles of raining, accretion, and reheating the halo, and you could think of this atmosphere really as sort of quasi-thermal equilibrium atmospheres. So I'll stop here. Thank you.
So we could take a few questions.
Yeah, so I have two quick questions.
Sure.
One on the larger scales. So the molecular and the cold clouds, to what extent, how extended they are? Because if you go to larger enough scale, the density is low, and then the time scales for cooling and molecular formation become very long. That's one question. And the second is on the smallest scale, on the horizon scale, you said that actually the black hole doesn't like to accrete the mass. So all this, does it matter? Because in the end, if there's a bunch of gas near the black hole and just decide on some other basis, other physical mechanisms, the black hole decides what would be the rate, does it matter at all this feedback and feed processes?
Yes, so I start on the last one. So yeah, it matters a lot because the flux that you have at different scales is determined by your macro scale halo, right? So once it arrives here, you are right. So if you go GRMHD, so you get re-ejected back. So you can actually, you're right, you can construct, say, one zone model, which is very simple. There's conservation of mass and energy throughout the phases. So in principle, over large time scales and large, say, spatial scales, you can assume this. But then we need to go down to the, to comparison with observations. And so over there, we need to zoom in into the different regimes. And so each physics is determining different processes. The first question was about molecular clouds, right?
Yes.
So yeah, absolutely. So the last phase is 100, you see here, right? So this is the hot X-ray phase. The warm phase is very easy, so to speak, to form and kind of extended. But at some point, only the very dense peaks here condense. So it's, I would say, rare event, but they start to form and then they pile up in the central region, right? So it's.
What's the physical scale on
this
image?
Is the zoom in of here is 1 kiloparsec. So it's not the same. So it's basically like
okay,
here.
okay.
Okay. So and this one is like here.
Okay, so that's really the inner parts of the galaxy. It's not the extended halo.
Correct. Yeah, yeah. This is the inner 1 kiloparsec, and this one is 100 parsec or 10 parsec.
Right. So I think we have to keep moving. Sure. So let's thank the speaker again.
Well, first of all, let me thank the organizers, the organizers of this meeting for allowing me to speak today about my research. My name is Jesus Salas. I'm a 6-year grad student at UCLA, and I'll be talking about my research about the dynamics of gas in the galactic center. So we've heard quite a bit of galactic simulations this morning in this conference. So we live in this spiral galaxy, Milky Way, and as we heard from Max, one of the most significant discoveries in astrophysics is that there exists a supermassive black hole at the center of every galaxy. And our galaxy is no exception. We live not in the center, but about 8 kiloparsecs away from the center, about 30,000 light years. And of course, this is not our picture of our galaxy. We don't know what it looks like actually from the top down. We can only look at it from the edge on. And it looks something like this. You've probably seen the Milky Way in a clear night, not in mountaintop. So I said there's a supermassive black hole at the center of our galaxy with a mass of about 4 million solar masses. And because the galactic center, the center of our galaxy, is the closest galactic nucleus to us, it is an excellent laboratory for studying physical phenomena that may occur in other galactic nuclei. And you can see the galactic center is very heavily obscured by interstellar dust. So we need to use infrared telescopes to see through the dust and see what's going on in the center. And if we look at this patch of the very center of our galaxy, in a region of about 1 degree in the sky, this is what it would look like. So this is an infrared image from the Herschel telescope, space telescope. Here is the supermassive black hole at the very, very center. This is a region of about 1 degree, which is about 150 parsecs from the black hole. And this region is called the central molecular zone. It is one of the largest, or the largest reservoir of molecular gas in the galaxy, containing about 30 million solar masses of molecular gas, mostly in the form of H2, molecular hydrogen. And it's condensed mostly in what we call giant molecular clouds, and we've heard what those are in this conference. The properties in this central molecular zone are very different from gas in other parts of the galaxy. It is about an order of magnitude more denser, and about also 10 times warmer than gas in other parts of the galaxy. Typical gas temperatures are 10 to 20 Kelvin in other parts of the galaxy. In the center of the galaxy, these are 70 to 100 Kelvin. And this central molecular zone is a very turbulent medium. And we know that the gas is kept this warm by the constantly dissipating turbulence. However, it's not very clear what drives the turbulence. I mean, there are several possible sources. Cell gravity is one. Inflows from the outer parts of the galaxy to the central molecular zone, that's another one. Of course, supernovae, a star formation in supernovae that injects large amounts of energy into the surrounding media. Another possible source. And there's a saying in astrophysics that when we don't understand something, we blame the magnetic fields. So, of course, we know that magnetic fields are also another source of turbulence. However, which one is the most dominant source, or to which degree each of these sources contribute, it is not clear. But nevertheless, to study the dynamics of this central molecular zone, we need to include turbulence into our to study this zone, we need to include turbulence. And the purpose of my dissertation work is, one of the questions that I try to answer is, what are the consequences of constantly driven turbulence in the dynamics of the central molecular zone? My goal is to understand how gas inflows from this zone into the very central parsec where the supermassive black hole resides. So, as I said, the central molecular zone is highly turbulent, and we know that it is the turbulence that prevents the gas from collapsing. Because if you have an interstellar cloud, gravity will just tend to collapse the cloud to form star or stars. However, in the central molecular zone, we know that is the high turbulent dispersions in the order of 15 kilometers per second prevents this from happening. And then also there's evidence that says that the turbulence plays a role in the suppression of star formation. And there have been a few studies that deal with global simulations of gas in the galaxy with turbulence by simulating star formation and supernova feedback. However, in my work, I take a different approach, which is I'm going to spend a few minutes talking about. So just to start with, these are an initial conditions snapshots of a simulation I did a few months ago. So I start with a collection of molecular clouds, because the galactic center is mostly composed of giant molecular clouds. Each of these dots, it's a giant cloud of about 8 parsecs in diameter. So these are quite large. Each of those clouds contains 10,000 particles. I use a code called Gadget2, which uses smooth particle hydrodynamics to solve the equations of the Euler equations of hydro, and it also includes gravity. So in total, I have 1 million particles. The gas is isothermal, and these clouds will move in the gravitational potential of the inner galaxy. This is 500 parsecs across the box, and this is the edge-on view. This is what we would use to compare to observations. Now, without turbulence, this simple simulation will not run. The gas is so dense, and the thermal pressure is not enough to counteract gravity, so it will just collapse. So what I've done is I included turbulence into my simulations. And the way I do this is by adapting methods are in the literature. There's two methods, but they're which are up there, but they both deal with turbulence by requiring Fourier transforms on a cubic box, on a cubic grid or lattice, with n cube points, right? And where n, typical numbers of n is 128, 256, etc. And this is to create a turbulent velocity field that follows a given power spectrum, P of k, where k is the wave number. And so this is image taken by one of Mordecai's studies in the late 90s. You have a box 128 with 128 points in the lattice. And you can see the box is filled with gas, and the gas is very turbulent inside. So let's remove the gas. I'm just going to explain a little bit of what's going on. So you have this lattice that has 128 lattice points in each dimension. And the size of these boxes don't have an inherent physical size. So for my work, if I wanted to use this method with a size L of 500 parsecs, and at the same time requiring to resolve the fine details up to a fraction of a parsec, then the number of points will have to be huge, 500, 5,000 or more, which will require massive computational resources. So I can't do that. But what I did, I created based on this, I did a workaround. So instead, what I did was to create smaller turbulent boxes, lattices, that have 128 lattice points per side, which is better for the computer, for supercomputer to handle. And these are 8 parsecs per side, enough to fit one typical cloud of the central molecular zone. And using this, I tile them up to fill the volume. I'm representing here my technique with a toy diagram. This is not the real thing. It's just a representation to give you the idea. Then I tile them up to fill up the area in this case, or the volume in my simulations. So that way I can fill up the entire domain, which is about 512 parsecs across, and at the same time keep the fine resolution of about 0.06 parsecs. And each of these turbulent boxes are drawn each of these turbulent boxes contain a realization of a turbulent velocity field with a power spectrum of k to the -4, which you will notice is slightly steeper than typical Kolmogorov turbulence, where the Kolmogorov turbulence is in this notation is -11/3. And the reason for this is that there are a few studies by Clark et al. In 2011 and others that claim that this slightly steeper power spectrum is more suitable for compressible gas under gravity. So that's the only reason. The power spectrum itself does not have a huge effect on these simulations, but to be consistent with the literature, that's what I use. And so my clouds will move through these many grids, and they will experience kicks coming from these grids, and I normalize all of them to maintain the magnitude of these grids are adjusted to maintain a constant energy input rate. And just going back to the initial conditions that I talked about before, these are the clouds, and they will move through these grids under the gravitational potential of the galaxy. So with that, I can show you the results. The important thing to notice here that I want you to remember is that without the turbulence, this simulation will not run. They will collapse immediately. But with this constantly injected turbulence, they're able to run for very long time scales. This simulation runs for 250 million years, and I can then study how the gas inflows to the very center. Again, this is 500 parsec box, and the black hole will be, you cannot see it, but it will be at the very center. Now, here is the top-down view of the simulations at different times, and you can see the filamentary nature that turbulence imposes on the gas, and at the same time, the gas is orbiting very fast, 100 in the order of 100 kilometers per second. So you can see the filamentary nature of turbulence, also shear at the same time by the orbital motion, and the turbulence creates the density fluctuations, which are then shear, which creates more, and it's a very dynamic process. Here's another. This top image is the edge-on view that we can compare to simulations, and you can see here that it can approximate the vertical structure that we observe in the galactic center. This is another infrared image from Herschel. The central molecular zone has this twisted ring shape, and my simulations are able to approximate that shape. However, after a few, well, this is overlapping the observations with my simulations, and you can see the resemblance here. Find the 10 differences. Now, but over time, the gas will settle into a flat disk configuration, which is expected in the absence of major perturbations. So this is obviously not what we observe in the galactic center, thus suggesting that there's a need for major perturbations, probably in the form of inflows from the outer parts of the galaxy to this zone, which I did not include, but it's a topic of my future research, which then suggests that the central molecular zone then is not in a dynamical steady-state configuration. And I'm good on time, so just to review my conclusions, the turbulence method that I showed you is able to support the gas against gravitational collapse in this scale. And it will be helpful for future studies of the central molecular zone. And lastly, my simulation suggests that the central molecular zone deviates from a dynamical steady state. Thus, we need some more major perturbations to reproduce more accurately this vertical structure that we observe. And that's it. Thank you very much.
Right, so we have time for some questions. Mordecai?
In your models, when you looked at them face on, and you showed the spiral filaments, you claimed that those were from turbulence, but they actually look like what you might expect from self-gravity acting on a differentially rotating disk, just like a galaxy as a whole. You had a movie, yeah. No, forward. Those look like two ray instabilities in a differentially rotating disk.
Yes, there's a combination. You have self-gravity, you have the differentially rotating, and you have turbulence, which
is supporting the disk.
Yeah, exactly.
But that's determining the level of your two-ray instability, but it's still two-ray instability.
Correct, yes.
Okay.
I did not go into much detail for the purposes of this talk.
Okay.
But you are correct, yes. Very excellent question.
Have any implication on the filaments seen in both X-ray and radio bands in galactic center?
I believe, are you referring to the non-thermal radio filaments that we observe? Is that what you're saying?
Yeah, I think it's non-thermal, yeah.
That will be a future step for my research. That's an excellent question. Those are tracers of the global galactic magnetic field, which has milligauss strength, which is not, it's significant. I don't include magnetic fields in the simulation, but that's a future step that we will include.
Okay. Mike.
Yeah.
So these perturbables, the molecular clouds, you call them molecular clouds, but the actual molecular clouds are much shorter lived. Yeah, so they survive like for 10 million years, or roughly that time scale. So can you comment on this?
I couldn't hear you very well.
So the lifetime of molecular clouds is much shorter than these time scales you're looking at?
Yes.
So can you comment on this?
Oh, yes. So what you're saying that the time scales the time scale of a molecular cloud is much shorter than what I'm showing right here. Yeah. And you're correct. If let's see, it did not play. Let's see, maybe. There you go. You can see that immediately before 5 million years, all the clouds are sheared by the differential rotation. And these clumps that form, they're not, their sizes vary, and they're very short-lived. With the contrast in the screen and the contrast that I chose to show this movie, you cannot see it very, very well. But these clumps, they go and disappear because of the shears, because of the turbulence, and the cell gravity. So you're correct.
Yep. In these simulations and in reality, is the coupling between the background turbulence and the motion of the molecular clouds, is that a one-way coupling? So are the from my world, if you think about particles in turbulence, there's a two-way coupling between the particle motions and the turbulent motions, and that's what your movie looks like. So I'm just asking is there a two-way coupling here? Are the particles reacting back? Is the particle motion affecting the background turbulence?
No, it's the...
These are not particles.
Well,
These are just tracers of the flow.
Yes.
It's just a way of tracing a gas dynamical flow.
Okay, so in reality, is there any coupling?
Well, in reality, no. Here is the turbulence that determines the motion of the small-scale gas.
In reality, yes.
Well, yeah.
But in the model.
In the model.
Okay.
No.
Any other questions, including over Zoom? If not, let's thank the speaker again.
Okay.
Thank you.
Hi, can you hear me? Okay. So normally I'm a theorist, but today I'm actually going to talk about an observational work I did recently on the detection of black hole-driven turbulence in the centers of galaxy clusters. So the speakers earlier in the session already gave a very nice introduction. Just to refresh your memory, galaxy clusters are clusters of galaxies that are gravitationally held together, mostly by the dark matter. And most of the baryons inside the galaxy clusters do not exist inside these galaxies either. Most of the baryons actually exist in between the galaxies in the form of diffuse ionized plasma that is called the intracluster medium, or the ICM. The intracluster medium usually has a temperature above 10 to the 7th Kelvin, so very hot, and it glows in the X-ray. The centers of galaxy clusters are what I like to call cosmic trash cans, because a lot of substructures have merged with the central galaxy or are in the process of merging. And just like this trash can here, the centers of galaxy clusters often also host a monster that is the supermassive black hole. So what I'm showing on the left is a Chandra X-ray residual image of the central region of a nearby galaxy cluster called the Perseus cluster. And you can see these cavities or bubbles that are created by the jets coming from the supermassive black hole in the center. And the younger cavities are also filled with radio-emitting plasma coming from the jets. So these lines are showing the radio contours. And this whitish feature, we think, is associated with a substructure moving around in the center of this galaxy cluster. So it's apparent that there's a lot of things going on, and the gas is clearly being pushed around by these processes. And it's reasonable to assume that just like in all the other astrophysical environments, bulk motion will decay into turbulence. And most people do believe that the intracluster medium is turbulent. But it turns out that it's not that easy to prove. So far, the best evidence comes from the Hitomi line broadening measurement. And Max Gaspari already introduced Hitomi. Hitomi was this X-ray telescope that made one observation before it tragically died. That one observation was looking at the central region of the Perseus cluster. What Hitomi told us is that there is a line of sight velocity dispersion of about 100-something kilometers per second. But because he told me it doesn't have good spatial resolution, that's pretty much all we know. And even though I'm a theorist, I know that X-ray telescopes usually don't have the best resolution. If you want best resolution, you want to use optical telescopes or even radio. Now, luckily, the central regions of galaxy clusters, just like the ASM, are also multi-phase. What I'm showing you here is the filamentary structure in the center of Perseus cluster that is seen in the optical, more specifically in the H-alpha. So H-alpha probes gas of temperatures around 10 to the 4th Kelvin, which is technically pretty hot, for humans, technically warm to the ASM people, but I like to call this cold because it's so much cooler than the gas that the X-ray observations are probing, which has temperatures above 10 to the 7th Kelvin. So it's like seeing ice cubes in a hot soup, which is kind of weird. And we don't fully understand how this cold gas gets there. According to my own numerical simulations, you can trigger thermal instabilities in a hot intercluster medium using AGN feedback. And then with the help of star formation, you actually make the cluster go through cycles of precipitation followed by AGN outbursts. But who cares about simulations when you have real data, right? And there's a lot of information there waiting to be extracted from the real data. So these days, a lot of the ground-based optical telescopes are equipped with something called the integral field unit. And what that does is, well, that allows you to extract a spectrum for every single pixel. So not only do you have the brightness of the pixel or the brightness of the lines, you also know the line shifts. So you know the velocity at which the gas is moving. And what I'm showing you here is the same map of the map of the same gas, but now I'm showing you the line of sight velocity of the gas. And usually when observers show a map like this, they'll say, oh, look, the motions of the filaments appear random or turbulent. Well, actually, there are simple calculations we can do to show whether or not it is turbulent. So in this past summer, I begged my observer friend to send me her data, and I computed the velocity structure function of the filaments. I'm sure you all know what velocity structure functions are, but just to make sure that you know what I did, it's a simple calculation. I go through this whole map, loop through all the pixels. For each pair of pixels, I record their physical separation and the velocity difference. And then I find the relation between pair separations and the mean velocity difference at that separation. So this is the first order velocity structure function. If you're interested, I can show you second order velocity structure functions later. So we do see a very beautiful parallel telling us that we're seeing turbulence cascade. So there's turbulence, no doubt. We also see flattening at some scale. And we all know what that means. That means that this is the beginning of the cascade, or this is the scale where turbulence is being driven. What is that scale? About 10 kiloparsec. Well, you're shaking your head. Yeah, we do. Wait for it. 10 kiloparsec happens to be the sizes of the inner bubbles here. Are we seeing turbulence driven by the feedback from the supermassive black hole? Well, some people aren't convinced. So I've also divided the filaments into inner filaments and outer filaments. The velocity structure function of the inner filaments is shown in red. As you can see, it's got a higher amplitude and even more prominent bump at the driving scale that I talked about earlier. Now, if you look at the velocity structure function of the outer filaments, shown in green, you can see that the outer filaments don't seem to care that much about this scale, which makes a lot of sense. because they don't feel the inner bubbles. So the power continues to rise towards larger separations. So it's possible that the outer filaments are probing turbulence driven on larger scales. And as I mentioned earlier, there's a structure moving around in the center of Perseus. So it's possible that we're probing turbulence driven by structure formation using the outer filaments. Now, I do think that there's a hint of a bump here, around 20, 30 kiloparsec, and that happens to be the scale of this outer bubble. So it's still possible that even the outer filaments are following turbulence driven by the black hole feedback, but it's just from a previous outburst.
Reference is all the H alpha?
Yeah, it's all just, yeah. Now let's look at another cluster, about 2597. What a great name. The same story. If we look at the inner filaments, the velocity structure function shown in red shows a bump at around 4 kiloparsec, and that happens to be the size of these inner bubbles highlighted with the radial contour. The outer filaments shown in green follow this velocity structure function. And there's a more prominent bump there, I think. It's more convincing in this case. And the scale is about 20 kiloparsec, which happens to be the scale of these outer bubbles. And this brownish curve shows the data obtained by ALMA that traces the CO gas, and it fits the optical data very well. Lastly, we also looked at the central region of the closest cluster, the Virgo cluster. Because it's so close that Muse only looked at the very center region, and we put in a proposal, so hopefully we'll get data on the outer region as well. So if we just look at the very center of Virgo, again, we see a beautiful parallel, and then it turns around at about 1.5 kiloparsec. And that happens to be the size of this inner cavity, and also this beautiful linear feature that you can see here in both X-ray and the radial. That is the jet coming out of the black hole. And by the way, the thickness of the line here is the uncertainty. So that's how beautiful the data is. Yes. But like I said, there's also the CO data. Oh, here's one CO data as well. This is tracing the molecular gas. So I hope that you're convinced that we're really detecting turbulence driven by black hole activities. Now, because we have such wonderful spatial resolution, there's more fun physics we can do. We all know that turbulence should dissipate on small scales. And that small scale might not be that small astronomically, because the densities are so low. It turned out that we're actually probing scales very close to the mean free path of the interstellar medium. So this is what you expect from dissipation, if dissipation of turbulence is due to isotropic viscosity. Earlier this year, my collaborator Irina Zhuavlova published a paper where she used the analysis of surface brightness fluctuations in another nearby galaxy cluster, the Coma cluster. And she said, well, if I see fluctuations on small scales, and if the fluctuations of the surface brightness is due to turbulence, then that means turbulence has not been dissipated. So that means isotropic viscosity must be suppressed. Now, because there's a lot of assumptions going into her study, not everybody believed her. And if we overplot our results, we actually find consistent results, right? So we see turbulence below where you expect to see turbulence if dissipation is dominated by isotropic viscosity. But our measurement is cheaper. I didn't use 12 days of valuable Chandra time. My data was free. And it probes even smaller scales. And we're not relying on any assumptions about the relation between surface brightness fluctuations and the velocity fields. we're probing the velocities directly. So it's providing the clearest evidence that isotropic viscosity must be suppressed in the intercluster medium. Now, if you talk to a theorist, they'll say, oh, duh, I always knew that. But for different reasons, if you talk to different theorists, which is very funny. If you talk to the plasma people, they'll say, yeah, it's because of plasma instabilities. And some other people will say, oh, you're just seeing alpha N waves. Regardless, the fact that we detect turbulence near the mean free path means that effectively the plasma is still collisional. And because obviously the particles are not directly interacting with each other, they must be interacting with the magnetic fields. So, to summarize, the intercluster medium in the centers of galaxy clusters is turbulent. And the turbulence is mainly driven by the feedback from supermassive black holes. We also detect turbulence near the mean free path of the intercluster medium. That tells us that isotropic viscosity must be suppressed and magnetic fields are operating on small scales. Thank you.
Right, so we have time for questions. Blakesley?
So there's been a lot of work done in the interstellar medium community on how you go from a position velocity, velocity dispersion, one dimension, to an actual 3D velocity power spectrum.
Yeah.
And so there's a lot of complications in like going from what's been called a spectral correlation function, which I think like Alyssa Goodman's group, like I don't know if Alyssa's still here, but yeah, her group was developing this like in the early like mid 2000s. Like it's not exactly tracing the velocity structure function, and so it might be interesting to kind of revisit some of that literature and potentially compare structure functions measured from simulations of clusters to the actual velocities. There's not a one-to-one there, is what's been found in H alpha in like the galaxy, those sorts of studies.
So I think that's a lot of points in that comment. So I agree, and I've been thinking a lot about how you should translate this into a 3D, or how do you translate between this 2D information, 3D information. Yeah. I think there's also difference between this and what the galactic ISM studies
have.
Yeah,
the slope of like 1/3 from like the point of view of the spectral correlation function doesn't necessarily translate to a velocity structure slope of 1/3.
So we talked about this a lot at the beginning of the project with Sia and other people. I think in the ISM studies, there's a problem with overlapping elements along the line of sight, and that's much less of a problem here because if you look at Perseus, there has been studies on what are the likelihoods that you're probing multiple components along the line of sight for each individual pixel, and there's good evidence that there's definitely overlapping issue in the central region, but in the outer region, it's not a problem. And the fact that we see very similar slopes for the inner and outer filaments suggests that overlapping filaments, at least in this case, it doesn't have a strong effect. Yeah.
The
same way, I'm not
use the mic.
Yeah, the same way you can just compute structure functions along one direction. It will be one-dimensional structure functions, which can be related to one-dimensional spectra. I think it will be quite useful for you. Another thing which you can do for free, if you can do one directional structure function, if you can compute longitudinal one and transverse one, the ratio of them in Kolmogorov turbulence is exactly 4/3. So you can see if it's incompressible or not.
Well, with this data, I'm not sure because it's not covering the whole volume.
You can, of course.
Yeah, but I forgot to answer the second part of your question or comment. So I am looking into my simulations as well. Yeah.
I wondered again, what's the effect here of the gas being multi-phased? Because as you go from a hotter gas to the cold, what you call cold gas, what I call warm gas,
Warm.
you go from through different Mach numbers. The Mach number changes,
Yeah.
and you might be seeing an imprint of just going
Yeah.
through this cooling length.
Yeah, yeah. So I'm a little surprised that nobody asked me why I'm not seeing Komarov. And since I thought someone would ask me that, I prepared the slides here. And we thought about the transition from subsonic to supersonic turbulence. So by the way, maybe this is the best plot to show. We see different slopes in 3 clusters, and they're all steeper than Kolmogorov. And one of them is more consistent with half, which is what you would expect from supersonic turbulence. But the other 2 are even steeper than that. So we sort of ruled out that as the main explanation for why we see a steeper spectrum. And we listed a bunch of possibilities. Maybe I do want to take the opportunity to show my favorite explanation, which Ethan doesn't like. So I'll mention these other possibilities that explain why we don't see a Kolmogorov spectrum. It's possible that it has to do with magnetic fields. Well, you know, when you run out of possibilities, you just say magnetic fields. But some people have said that maybe magnetic tension can even prevent the G modes from decaying into turbulence. And maybe we're seeing partial dissipation, again, due to magnetic fields. And plasma, people like to say, oh, maybe it's plasma instability, because, you know, everything is plasma instability. My favorite explanation is actually simply that black hole feedback is not a good driver of turbulence, because everything is changing on very short time scales, basically shorter than the eddy turnover time. So from the driving scale to the strength to volume filling factor, the ages of these bubbles are only on the order of 10 million years, whereas the eddy turnover time on the larger scale is on the order of 100 million years. And so I think I understand black holes, because, you know, bad drivers.
Right. So with that, I think we should thank all our speakers again and have coffee.